Welcome. This is Coach Dorf. Today, we're going to continue our discussion about derivatives. What are derivatives? So as a review, if I have the graph of a function, y equals f of x, and I have a point, x equals a, that's going to give me a point on my curve that has the value x equals a, y equals f of a. And I'm interested in the tangent line to that point at a, f of a, and in particular, I'm interested in the slope of the tangent line. The tangent line is the line that only intersects that blue curve at one point, at that red point there. It only intersects it at one point when I'm really close to that point. So I only have one point on the blue line that I can use. And that slope of that is going to equal the derivative at the point. So that's what the idea of the derivative is. Then how does that then leads us to what is called the definitions of the derivative. So definition, so the derivative of a function y equals f of x at the number x equals a is given by the limit as h goes to 0 of f of a plus h, let me write it, f of a plus h minus f of a all over h, and that's going to be the derivative at a. I can also write that as the limit as x goes to a of f of x minus f of a over x minus a. That's also known as the derivative. And this symbol here, these symbols mean the derivative of f of x at x equals a. And this fits in with the image or the diagram here that I wrote. If I take another point, so on the blue line, to find the slope of the green line, we only have one point on the blue line, and we would need 2 points. If we were to take a second point here, and we look at the slope of that line there, this is the slope of that line, and that's going to equal the differences of the y's over the differences of the x. And so if I call this point just here x, this is going to be f of x minus f of a over x minus a. That's what that slope is of that purple line. And that's exactly what we have here. Why do we have the limit in front of it? Because we want that purple point to get closer and closer to the red point. And so we're taking the limit as that point gets closer and closer to the red line. And that's why we get this limit here. All right, so that's where if we do that in the limit, then we get the slope of the green line, the slope of the tangent line. And this is the beauty of calculus, right? We couldn't do this before calculus. We could find the purple quantity, the slope of that line, which is also called the secant line. We could find the slope of that line because we'd have 2 points, but that wouldn't give us the slope of the green line. We needed the idea of limits to do that, and by doing the limits, then we can get the slope of the green line. And now you may be asking yourself, why would I even be interested in the slope of the tangent line? Well, it turns out that the slope of that tangent line, or the derivative at that point, has many, many applications in STEM fields. In particular, for example, here's one example. In data science, if you're looking at trying to figure out a way for a computer to learn and solve a problem here using artificial intelligence and machine learning and data science, what you need is actually you're taking the derivative, and that's all hidden behind it, but it's what makes it effective. All right. I'll also talk maybe later, the derivatives were also used, this kind of idea was used in making some Disney movies to make characters that were animated. There's lots and lots of applications of these ideas of derivatives. And so that's why we're interested in it. And the theory behind it is that we've got this slope of the secant line, and then we take the point closer and closer, the second blue point closer and closer to the red point that we're trying to find here. And that gives us the limit, and that gives us the derivative. The first definition here, this green one here on the circling in green, is equivalent to it, where h just represents the distance between the x point and the red x point and the purple x point. So h is just that distance there, and as that distance gets closer to 0, then your red point on the blue graph and your purple point on the blue graph are getting closer and closer to each other. So there are equivalent ideas there. All right, what we're going to be doing this is we're using this to find the equation of a tangent line. So let's see, let's review this. What's the equation of a line? Well, if we've got a point x naught, y naught is a point on the line, and m equals the slope of the line. Then we have the equation of the line is y minus y naught equals m times x minus x naught. All right. You probably saw that earlier in high school and college in high school algebra. The way we apply it here, so for derivatives, what we're going to do is we're going to let x naught equal a, then y naught is going to equal f of a, and the slope is going to equal the derivative of a, where y equals f of a is the function we have, and x equals a is the number, and f prime of a equals the derivative of f at a. So in particular, we'll use for the equation of the tangent line for equals f of x at x equals a, we'll use this minus f of a equals the derivative times x minus a. All right, so let's do an example. Let's example 1. Find the equation of the tangent line to y equals f of x at x equal 2 if f of 2 is 4 and f prime of 2 equals 3. So we're going to use this minus f of a equals the derivative prime of a x minus a there. So here we have a equals, well, they don't tell us what a is, but it is really, I guess they do tell us there. It's right there. A is 2. So that comes from this part here is 2. Then we have f of 2 is 4 coming from here. And we have the derivative is 3. And that comes from this part right there. So then we've got minus f of a equals f prime of a, x minus a. So we have y minus f of 2 equals f prime of 2, 2 minus x minus 2. So we have y minus 4 equals 3 times x minus 2. So now I'm going to distribute this 3, both terms here, and I'm going to get 3x minus 6. And then I add 4 to both sides, and I get 3x minus 2. And that's my equation there. Now we can go the other direction, such as in this. If the equation of the tangent line 2 equals f of x at x equals 3 is given by y equals negative 2x plus 3, find f of 3 and f prime at 3. So it's important to know, to understand here, I can only find this tangent line here only is valid, only works at x equals 3. That's the tangent line at x equals 3. If I take a different point, like x equals 4, I'm likely going to have a different equation for a tangent line. But it's okay in this problem because we're trying to find f of 3 and f prime of 3. So go ahead and do this in blue now. So we're given y equals negative 2x plus 3. The negative 2 here, that represents the slope of that tangent line. And that slope of the tangent line is the same thing as the derivative at 3. Again, this only works, that is the slope at x equals 3. Again, if I took a different point like x equals 4, I'd have a different value for the slope of the tangent line. So I couldn't answer this question if they gave you this information and they said find f prime of 4. But I can find f prime of 3 because I have the equation for the tangent line. So we know that f prime of 3 in this problem is negative 2. All right, what is f of 3? Well, here, what I'm going to do now is I'm going to take y equals negative 2x plus 3. Y is the same thing as f of x, like this. And so now I'm going to substitute x3 in for x. Oh, sorry. Let me rewrite that here. My eraser up here. See if I can do that nicer. Substitute in 3 for f of x. All right. Use in this equation here. So now I'm going to have f of 3 is going to equal negative 2 times 3 plus 3, which is going to be negative 6 plus 3, which is going to be negative 3. So f of 3 is negative 3, like that. Good. All right. Another way to do this here then is we can think of limits. So we can think of limits as derivatives, certain limits as derivatives. And that's because because of the way the definition of derivatives is written. So recall definition of derivatives. We've got two of these. First we have the derivative at a equals the limit as h goes to 0 of f of a plus h minus f of a over, and then the second one is the derivative of a is equal to the limit as x goes to a of f of x minus f of a over x minus a. All right, so let's look at an example for this one. And this example here, we'll say each limit that I'm going to write represents the derivative of some function f at some number a. Find f and a. All right, so let's suppose I'm given this one, the limit as x goes to 1, 10 to the x to the 10th minus 1 over x minus 1. So I'm going to say which one, this is going to be one of the definitions of the derivatives. Is it number 1 or number 2? So the limit in part A is similar to definition of derivative number 2, like that. All right, and so I'm going to compare those two. And what do I notice? So in the one that's given to me here, we have x going to 1, and here we have x going to a. So we have x going to 1 and x going to a. Well, this means that a is going to equal 1. That was pretty straightforward there. We can also see that here in the green part, we have a 1 there and we have an a there. So now we need to figure out what f of x is. What is f of x? Well, I will look here. I've got f of x listed there. I've got x to the 10th. We have f of x equals x to the 10th, because I'm just going to compare those there, looking at what I've given, using those two, the definition number 2 and corresponding the parts there. And then the last thing I'll do is I'll check this. Let me use a different color here. I haven't used green. So check if I'm given this, the limit, well, let's use the definition, limit as x goes to a of f of x minus f of a over x minus a. So I substitute these in, I get the limit as x is going to what? So we're saying a is 1. So here I'm going to put in a 1. And then f of x we're saying is 10. So we're going to put in the x to the 10th, put x to the 10th in there, minus f of a. So that's going to be 1 to the 10th. And then that's all over x minus 1. And if I simplify that, I get the limit as x goes to 1 of x to the 10th minus 1 over x minus 1. And this matches the original problem, which was given right here. And I need a different color. Oh, color. I guess we'll use orange here. This here matches this here. So that's what my check. So I know it's right. So f of x equals x to the 10th and a equals 1 in this problem here. All right, let's do another example of that. We'll do part B. Part B, suppose I have the limit as h goes to 0 of 2 plus h cubed minus 8 over h. All right, so which definition should we use? Well, I'm going to use the one where h is going to 0 of, we write that there, f of a plus a minus f of a all over 8. So why do I pick that one? Well, they both have h's in them, h going to 0, and there's an h in the denominator. That's why we choose this one. So now we have to compare things. Well, what do we got here? We know that 2 plus h cubed is going to equal f of a plus h. Looking at those, I'm going to guess that a is going to equal 2 because of this and this there. And I'm going to guess that f of x is going to equal x cubed. And that's because of, I've got what's inside the parentheses. I got a parentheses cubed here. So to me, that's like an x cubed. So the x is the inside part, the cube part is the cube part there. And now what we'll do is we'll just check. We have f of x is x cubed and a is 2. So we got the limit. We use the first definition. We'll plug these numbers, substitute these numbers in and see what we get. So the limit as h goes to 0. When I do f of a plus h, this is going to be a plus a cubed. Because remember, if a little side here, if f of x equals x cubed, then when I put a plus h in here, that's going to go into that what's inside the parentheses, and I get this. Going back here, then now I have f of a. What's f of a? So if f of x is x cubed and a is 2, then f of 2, which is f of a, is going to be 2 cubed, which is 8. So I'm going to get 8. Oh, sorry, let me rewrite this here. It'll be a cubed over 8. Now we're going to go down here. And so then I'm going to get the limit, substituting in a here, I'm going to get 2 plus a cubed minus 2 cubed over h, which is the limit as h goes to 0 of 2 plus a cubed minus 8 for h. And if I look at this one, then remember my original problem was this, and now I've got this, and these two are the same. This matches the original problem. So I have f of x is x cubed and a equals 2. All right, so now let's talk about then some of the meanings of derivatives. So how are these sometimes represented in word problems? So let's suppose I have this problem here. Water is flowing into a large spherical tank at a constant rate. Let h of t be the height of the water in the tank. What is true about the h dt? If you want, you could have there's an image. Here's my tank, and it's spherical, so it's the shape of a ball, and I've got water inside of it that's being poured inside. There's my water, and the height there, this represents the height of the water. All right, so what's true about dh dt? Well, first of all, what's true about, let me just write this down, what's true about dh dt. So dh dt, is it positive or negative? Is the height changing with time? So this represents the change height with time. So as time progresses here, what's happening to the height? Well, it's getting larger because we're adding water to it. So dh dt is going to be positive. It's increasing. All right. Is dh dt constant? Is the height constantly changing throughout the time I'm adding the water in? Well, think about it. I'm pouring water into this spherical tank. Does the height change constantly? The answer is no. No. HDT is not constant. Why is that? Well, when the water is low inside the spherical tank, the height is increasing more rapidly. As I get near the middle of the tank, because the tank is wider, the height is not increasing as much. The water is being flowed in at a constant rate. So at that constant rate, at the very bottom of the tank, the height is increasing more rapidly. As I get near the middle of the tank, which is wider, the height is increasing at a lower rate. So it's not constant. How would this change what if the tank were a cylinder? Let's see, can I spell the word cylinder? Let's try again. For a cylinder. So now the tank looks like this, and you've got the water in there, and you've got a height. So what is true about dh dt? Well, dh dt is again positive because we're adding water in at a constant rate, and dh dt is constant because the width of the cylinder is not changing. It's going straight up, so that they're both the same. What if we have our spherical tank again, and we're going to let V equals the volume of the water in the tank? What is true about V dt? Is dV dt positive or is it negative? Well, it's positive because you're putting water into the tank. So the volume is increasing as you put more water in. Is the volume constant or is it increasing? Is it constant or non-constant? Or I should say, is dV dt constant? Yes, dV dt is constant because the water is coming in at a constant rate. So the volume is increasing at a constant rate. Let's do another example. Let's see, let h of t be the daily cost in dollars to heat an office building when the outside temperature is T degrees Fahrenheit. What the meaning h prime of 58? What does that mean? So H is the daily cost to heat the temperature, to heat the building when the temperature is 58 degrees. So here, so H prime of 58 equals the rate at, oops, the rate at which the daily heating costs changes with respect to temperature when the outside temp is 58 degrees Fahrenheit. The derivative represents, we've talked about it as the slope of the tangent line, but it's also the rate of change. So the derivative of 58, the derivative H prime, the derivative of H represents the rate of change of the temperature, and H prime at 58 is the rate of the change of the cost when the temperature is 58 degrees. And notice that note F prime of 58, the units uses units of dollars per degree Fahrenheit. How about this one here? Let's see, would you expect H prime of 58 to be positive or negative? You don't know, but let's see if we can figure that out. So what is H prime? It represents the rate of change of the daily cost at a certain temperature. So suppose the temperature outside is 58 degrees, and we're looking at the rate of change is now, if the temperature keeps increasing, how do you think the heating costs are going to be? Well, if the temperature is increasing outside, then the cost for heating it is probably going to go down because they're going to do less heating. So I would say H prime of this is going to be negative, because as the temp outside increases above 58 degrees Fahrenheit, there is less need to heat the building. So the cost to heat will go down, meaning H prime of 58 is negative. All right, last thing I want to talk about today is what's the graphs of a function of f and its derivative. So let's see here. Suppose I have a graph of a function that looks like this, and I'm going to put in some values here. We'll call this -1, this x equals 2, this equals 1, this is x equals 2 here. So, and this is the graph of y equals f of x. And now I want to look at the graph over here, -2, -1, 1, 2, and I want to look at the graph of y equals the derivative. All right, so what is derivative again? Is the slope of the tangent line. So I'm just going to take some points here. If I take this point here, here's the tangent line. This has negative slope. So I'm going to be down here for the purple graph somewhere. I'm going to be down here, down in the negative part of it. If I keep doing these, I'm going to be negative all the way down here for all these until I get to here. And there we have slope equals 0. So when I'm drawing the curve, the curve of the derivative here, I should be negative until I get to this, because that has x equals 0. So this is, sorry, y equals 0. So this is the derivative, which is y, is 0. And that matches up this, matches up with that right there. But these over here, where I have these red curves, these red tangent lines, those slopes are negative before that. So over here on the graph of the derivative, these should all be negative values, meaning these are negative values for y prime, or sorry, for f prime, which equals y. So the y values should be negative, and the y's, that means they're below the x-axis. These are where you have negative y values, right? Because there's y is -1, y is -2, y is -3. Now, I don't know the exact values along the purple curve for the derivative, but I know that they're negatives. Now go back to the blue curve here, and I'm going to pick another color. Let's pick green this time. What happens to the slope of these lines here, of these tangent lines? Well, those are positive slope. So that means in my purple curve, where is positive slope? That's over here somewhere, right? This is where positive y values. And again, y is the derivative. So I'm going to be up here somewhere to correspond with the green values over here. That's going to correspond over there. And I notice when I get to the point right here, which is about x equals 2 for the original curve, that has a 0 slope. So over here on my derivative one, I'm going to have a 0 here. And so I'm going to fill in my green ones and just make it look something like this. Positive values here for the purple one, because the corresponding green curves, the slopes of the, when I look at the blue curve and I look at the green tangent lines, they have positive slopes. So these purple ones should be positive. And then finally, go back over here. If I look at my slope of my tangent line, when x is larger than 2 for my original curve, they're negative. So over here in the purple, these should be negative. So I get something like this. Let's do another example of this. Suppose my curve now looks something like this. We'll call this point 1, -1, -2, 0. Here's 1, and here's 2. Y equals f of x. And we want to look at the graph of the derivative. So we're going to call this y equals the derivative. What do I notice? Well, I'm going to go ahead and do where it's 0, because that's the easiest. So here at x equals 1, the slope is 0. So that means I'm going to have on my curve over here, let me put in my points, it should be 0 at x equals -1. Likewise, I'm going to have 0 here at 1, so that should be 0. And at 0, I have 0. All right, so now let's look at in between those parts. What happens when x is less than -1? I draw in my red tangent lines there. Those are positive slope. So over here, I should have positive values for my f prime curve. Then when I do between -1 and 0, I have negative slope. So I should be below the x-axis on my derivative curve. So I should have green should look like that. And I know I have to go back to 0 when x is 0, because I have that yellow or orange line in the original curve. The tangent line is 0, which shown right there. Then I go back to my between what happens when x is between 0 and 1 on my original curve. Well, I've got positive slope again. So I should be positive on my graph of my derivative. And when x is 1, I know I have 0, so it has to connect up like that. And then last, when x is greater than 1, I've got these green tangent lines on my original curve, and those have negative slopes. So if I go over to my graph of my derivative, they should be below the x-axis there. So there's my graph of my derivative curve like that. All right, hopefully that helps you. Have a great day.